Are you at home or only Ahmed? Only Ahmed. All right. Okay, no problem. So you are in the school. So is it is today still a holiday or not? Maybe today is still Eid holiday or just all right. Okay. So no problem. Let's start our meeting. And I'm sorry about the last meeting. I really forgot about the class because I was busy. Like, never mind. So let's discuss for today's contest. And before we start our discussion, let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Rabbana zidna ilma warzuqna fahma. Amin. And happy Eid Mubarak everyone. And let me share my screen. So today you you did the Celtic Olympiad in informatics, and there are three problems, and I think it is easier than the last contest since there are some there are more users solve it. And then maybe let's start from the first one. I think both of you got accepted on this problem. So what is your total score or your best score for each problems? Can you mention three scores? Okay, that's good. And then all of you got accepted on the first one. So how was your solution? Okay, maybe all of you can try to explain just the general idea. Okay, who will explain first? Maybe TJ, will you explain? You can explain through the mic of the chat. Yes.
Sir, sir, what I did was I got all the invariants for each of the cyclic shifts. So there are n cyclic shifts, so there will be n queries. And
Yeah.
then we can say that when x is at the first position, we can see the number of invariants, and when it is at the last position, we can see the number of invariants. And then the difference between them will be uh, the number of greater elements minus the number of lesser elements than it. So
Yes.
we can, this number will be is different for everyone. Like it, there was a pattern like minus n plus 1 and so on. So it just becomes a simple formula that which one is this one.
Yes, that's correct. So how about Anik? Is it same or not? Same, all right. Asking the cyclic shift. All right. And how about Saram?
Sir, my solution was a little bit different.
Okay.
What I did was the first query was 1 to n, and the next query
Yes.
was uh, the prefix would be same, but suffix would be reversed.
All right.
So I did this for each suffix.
All right.
So using this, uh, I, we can calculate the number of invariants in each suffix,
Yes.
and so what I did was, uh, let's mm, initially I have the answer as n, and then I can, using these values, I can calculate what is the position of n minus 1 in the array. So, and similarly, if I have a suffix, then using these values I can calculate the position of I I in it. So I just keep adding values like this, and at the end the whole permutation was created.
All right. Yes. Yeah, that's correct as well. Okay. But I think the cyclic shift is simpler. All right. And my solution is curing I and then, or maybe start from X and then 1, 2, 3, 4, skipping X and so on until N. Okay. Actually, the general idea are same, but we can use different type of query. And of course, we need ON query, right? Because N is 4,000 and the maximum number of query is 4,000 as well. All right. Okay. So just query like that, and then we got some formula. I think for cyclic shift, we can easily know how many number before that, so we can directly place it to the answer. While my solution, if I do this, I can only know the order or how many number before x from 1 until x, like that. So I need to keep inserting to the answer. All right. So I think cyclic shift is simpler. All right. Thank you very much for the insight and the alternative solutions. So is there any other question about the first problem? All right. Then let's, yes. All right. How many elements are before I? Yes. So I think it is same as my solution. We need to insert, but the formula is different and the type of query is different. All right. So let's continue to the next. Okay. TJ got 30 point for this problem. So how was your solution?
Sir, I solved first. I coded for n square. Like if we do n square, then it solves the subtask 2. I thought that it will get subtask 3 as well, but it did not. And then I made some observations and I got the solution for subtask 5 as well, and I coded that.
All right.
I knew the solution of subtask 4 as well, but there was a little less time left, and I was not getting accepted at order and scare like the subtask 3, so I did not code that.
All right. Okay. For the others, do you got the second subtask or which subtask you got? I think Saram and Anik got 10 points. So is it the first subtask or second? Second one. Which one you got? I think the second one is easier, right? Okay. Wait, do you have a problem with your internet connection? All right. Okay. So I think Saram and Anik got 10 points, right? So which subtask you got? The second one or the first one? All right. Yes, that's great. How about Anik? Did you get second subtask as well? Okay. So the problem is like this. Given the starting events and or let's say the starting node and the target node, and we can move from a node to another node if and only if this inequation is satisfied. So we can go from x to y if like this. If ex is between, basically it's like this when the endpoint of x is between the range of y, right? Okay. And it is hard if the rule is like this. But actually, we can reverse the direction. What if we want to go from E to S? we want to go back from E to S. From node E, we want to go to S, but we can go from Y to X if and only if the endpoint of X is inside the range. All right. Is it understood? Okay. And inversing the direction will make the problem easier. All right. Why? Because we can go to the other node greedily. We will always go to the node with the minimum S. How do you think? Is it always optimal? So for every node that is ended in inside this range, we can choose any of this node, right? But the optimal one is taking the minimum S. All right. So it means for each node, we know which node is best the best node to jump at, just like the parent of this node. So now for each node has a parent, so it become a forest, right? So when we want to go from E to S, we can jump to the parent and to the parent and so on, right? To its ancestor, as long as the the S of the node, the S of the ancestor is greater than this. It is still greater than ES like this. So it means if it go to the parent and now the S of the parent is less than or equal to E, it means we always can go here, right? All right. So just go to the ancestor until the value of S is less than or equal to ES. All right. Is it correct? How do you think? This idea is correct or not? If the parent doesn't exist, impossible. Yes. The parent doesn't exist means there is no node starting from this to this. So it means we cannot go further. So it is impossible. Because we always take the farthest, right? So it means we cover these points. We can go to any node that the endpoint is between these segments. So it means if mm, there is no parent after this, it means we can only go here. cannot go more than this. So it means it is impossible. Or if E is before S, then it is also impossible. All right. Okay. Is there any other questions? I mean, if the ES is greater than EE, okay, it means it is impossible. So ES should be less than or equal to EE. All right. Is there any question about this idea? Okay. Then then let's go to the detail. At first, how to know the parent? Do you have any idea how to get the parent of each node? For each node, how to get the parent? Parent means among a node that is the end of the node is inside this range, and we will choose the minimum s. For example, like this, we will choose this one. All right. So will we use line sweep? So can we use line sweep? In fact, if we sort based on L, then the value of R is not sorted. Yes. So how do you think? We can use this or not? Or do you have any other idea? Wait. Okay. If I think the parent always has the smaller starting point, because if the starting point is higher, then it is redundant. No need to go there. Okay. Just keep it as a root, and then there is no parent for this node. So how to use line sweep? So what is inside the set? Can you define the set? What is the value inside the set? And not that the range is not sorted. I mean, if we sort by L, the value of R is not always sorted. Sometimes it is unsorted. The starting points of interval that is still open. What do you mean open? Is it in the range? In the current range? So should we sort the intervals? If we need to sort them, then based on what? Based on L or R? Alright. Okay, so no need to sort them. Only push the starting point of node 1, for example, like this. And this is the end point for the second. Is it what you mean? And we will sort them together. Alright. Okay. So when we are here, it means the open intervals are L 1 and 2, right? And what can we conclude? What can we conclude from this? How to get the parent of 1? Of course, the parent of 1 is 2, right? But how to know that? Okay. Do you know the definition of the parent? Okay. How can we know that the parent of 1 is 2 from 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 this line sweep? Okay. Yes. No problem. Okay, let's continue. So from this line sweep, how can we know that the parent of 1 is 2? When we can conclude that? I mean, when we are here and the open, yes. So when we are here, then what is inside the set is the starting point of 2 and the index maybe. We need to store the index as well, right? And let's use LNR. This is the starting point of 2 and the starting point of 1. And the starting point of 1 is greater than the starting point of 2. And then from this set, what can we conclude? Can we know the parent of 1 or the parent of 2? All right. Iterate in reverse order. All right. I see. All right. Iterate in reverse order. It means we will iterate from this. When we reach the starting points, so it means we just check all segments. Wait, all segments here. Yes, I think it is still incorrect. Wait, how can we prove that it is incorrect? If we only check here, okay, yes. Sometimes R is greater and we should not use this. Yes, okay. TJ got an idea and that is the same idea as mine. We use segmentary. Yes, we will use segmentary. Okay. All right. So for each segment, okay, let's say we have segmentary, and for each E, we can update the S, right? For each E, we can update the S, and then just update for every segment. And then just iterate again for each segments. We will take the minimum value around this range. And we got the minimum value. All right, this is understood. But we need compression since this is large. Or you can use dynamic segmentary as well if you avoid the compression. But I think compression is better. All right. Yes, compression is better because the complexity will be log n, not the depth is log n, not log 10 to the 9. Yes. All right. So just use basic segmentary. No need lazy segmentary, right? Because the update is only point update. All right. After getting the parent, then how to go from E to S? If we just go to the parent one by one, then it is slow. Then how to make it faster? Yes, just use binary lifting. So we can use parse table to store the first parent, second parent, fourth parent, eighth parent, and so on. And then just do binary lifting. All right. So as long as the to the power of something parents is still greater than RS, so just jump to that node and so on until we cut the last node that is still greater than RS, and we can jump one more and then jump here. All right. Is there any other questions? So that is the full solution. All right. So let's continue to the next one. Wait. Okay. Because if we go from S to E, we cannot use greedy, right? How do you think? If we go from S to E, can we use greedy? So let's say this is L, this is R. So which node we want to jump? We can only jump here, and we don't know which one is better because we don't know which R is correct. For example, if we just go here, then it is not always optimal because what if the target is here? LENRE is here. So don't go to this node, but we will go to this node instead. So we cannot jump greedily. But if we reverse the direction, it means for every segment, we can use any segment here. So it means the the longest segment is the best. just go there because it covers more segments. All right. So that's the reason. So we can solve it usually. Yes, I mean the smallest s. So the range will be the combined range will be longest. All right. All right. Is there any other question? And now this is the hardest. Wait. I think none of you got points here. All right. So what is the difficulty? Sorry. What is the difficult part? Why this problem is difficult? All right. Yes, for this case it is small. Can we use knapsack? Minus, yes. The value can be minus. All right. Do you know how to create an array that we can access negative index? I think for the implementation for this problem, we need an array of negative index, right? Yes, you can see it. So wait, I think this is the previous problem about segment repeats. Let me erase it. All right. So for example, we have an array. The size is 2 times maximum n. And we can create another pointer, for example. A is equal to AA plus maximum n. All right. So now we can use a minus 1 like this. Okay. Let's try this. Okay, is it correct? Have you ever used this trick? Actually, a minus 2 is equal to a or sorry, double a maximum n minus 2. All right. Yes, me too. I also usually use like this, but my friend told me this way, told me about this way. All right. Okay, so After this, you can use this trick instead of always adding maximum n. Alright. So this actually array is just like a pointer of integer, and these operations means go to the next pointers like that. Yes, welcome. That's why when we sort the array, we usually sort like this, right? This is the pointer. For example, like this. And for this, since there is a negative index, we can do this as well. We can sort from negative 60 to positive 60. All right. So a minus 60 means this equal to this. The address of AA, I mean the address of a minus 60. All right. Okay. Sorry. The prayer times has come in my city. So let's have a break in around 30 minutes maybe. And we will continue the discussion after that. All right. Yes, thank you very much. Assalamualaikum. All right, let's continue. Assalamualaikum warahmatullah. Okay. Okay, let's continue to discuss this problem. And Saram try to attempt using knapsack, right? But why it is wrong answer? Do you have any idea why this is wrong answer? Okay. So you use map to make negative number. So what is the maximum uplift if M and A is up to 50? It means the maximum uplift is 50 times 51 divided by 2. Is it correct? Or yes, I think this is the maximum uplift. How do you think? Should we make it greater? Maybe we can make it 100,000. All right. What if you add another zero here? Is it accepted on the first subtask? Okay. I think it is Saram's solution. All right. Yes, maybe if you want to use knapsack, you need to make it 100,000. And 10,000 is not enough. All right. And the full solution also use knapsack, but we use another greedy. Okay, but for the knapsack part, at first we can optimize like this. For example, how to solve this? How to solve M up to 100? Okay, wait, maybe let's solve m up to 30. If in subtask 3, the value of a is not bounded, it means a can be up to 10 to the 12. So if we use knapsack directly, it will be slow, right? Okay. So do you have any idea how to make it faster? All right. Do you know this idea? For example, if for a specific uplift, the number of items is 24, or let's say 1,000, for example. If we add the value one by one, then it is slow since we need to add 1,000 item. Is it correct? Or do you know the knapsack problem that each kind of item can be more than one? For example, given an item and we have knapsack with size M. For each item, we know the value, we know the weight, and we know the number of items with this type. Do you know how to solve it? For example, M is up to 1,000, N is up to 1,000. Value is can be a billion, and the weight is up to 1,000, and the count is up to a billion. How to solve it? Okay. So I mean, let's solve another simpler problem. Given a knapsack problem, we have n items and and what? And knapsack with weight m. And for each item, we know the value and the weight and the count. So how to solve this? Do you have any idea? If there is no count and the number of item for its type is just one, we can solve it with TP. Is it correct? How do you think? Is it understood? How do you think about this problem? So the original knapsack problem is like this, right? For each item, there is only one item. For each type, there is only one item. So we can solve it using two-dimensional TP, TP and M. right? And what if for each item there are infinity, for each type there are infinity number of items? Then it is just like coin change problem, right? Coin change problem. And again, we can solve it in NM using two-dimensional TP. Is it correct? Do you agree with this? When for each item we can use it many times, can we solve it using two-dimensional TP? Just like coin thing problem. All right. Then what if the number of item is not 1 and not infinity, but given in the input? And the maximum number of item is 10 to the 9. Then do you have any idea? Okay. What if the number of count is only up to 10? Then how to solve this? Okay, yes, that's correct. Okay, if the maximum value of count is only 10, then we can just solve it using knapsack problem, but for each item, we will repeat it 10 times, or we will repeat many times. And that's correct if the value of count can be very large, then we can divide into some parts. So let's assume, for example, there is a value v, the weight w, and the count is for example 100. Then we can divide into some parts. The parts are VW1 and then 2V2W1 and then 4V4W1 8V8W1 60V16V16W1 32V32W1. What else? After that, 37V 37W1. Right? Wait. One more 32. All right. Yes, I think just make it 37. Not okay. So it is just like creating 1, 2, 3, 4, 5, 6, 7, 7 items. I mean lock items, right? Just like creating lock item. So for example, we use this and this. It means we use this item 10 times. Is it correct? And for each number from 1 to 100, we can make the value from it, from this. Is it correct? Okay. Because it is binary number, right? Binary representation. And if it is greater than 37, then just make it 37 and add by the binary number. All right. So we can solve subtask 3 maybe, and the other subtask. All right. But what if m is large? For example, 300. Of course, we cannot make the state m cubes, right? If the state is m cubed, so it is 2e7. Then we cannot do another transition. All right. So how to speed up this solution? At first, we can do it greedily. Since we want to maximize the number of items or the number of pieces. So it means, what if we take everything? What if we take everything? For example, I think for 0, just take everything, right? How do you think? Is it always optimal if we take every number with 0? Okay, yes, of course. And then for positive, let's say the total number of items is P, and the total number of item in negative is A. I mean the total uplift. All right. So it means if we take everything, so the uplift is P minus A, right? If we take everything. And the maximum uplift we can get is P. And the minimum uplift we can get is minus A. Is it correct? So it means if L is greater than B or L is less than minus A, it is impossible. L should be between minus A and B. All right. And let's divide into two cases. The case where L is greater than B minus A, and the case where L is less than B minus A. All right. Okay. If L is greater than B minus A, it means we need to increase the value. How to increase the value? We need to remove some negative, right? And actually the second case is just using the same idea, just removing the plus because it is symmetric. And if we do it greedily, which one we will remove? The minus 1, start from minus 1 or start from minus m? How do you think? If we want to increase the uplift, by removing the negative items. We will remove -1 or remove -m. Which one is better? How do you think? We want to maximize the number of pieces. And unfortunately, we need to remove some pieces to make the total uplift is exactly L. So which one we will remove? Start from -m or start from -1? The intuition is like this. If we remove -1 to make it exactly L, so it means we need to remove many items. But if we remove -m, it means we only need to remove some items. Is it correct? So which one is better? Of course, -m is better. Do you agree with this? Because we just need to remove few item and we still have many items. So we can just greedily remove from -m and minus m plus 1 and so on until or as long as it is still less than L. So we will add plus m like that and then plus m minus 1 and so on until if we plus that value, if we add that value, the value will be larger than L. So it means just stop at that point. But now the current uplift and L, the distance is small. Of course, the distance is less than M, right? Is it understood? Is there any question? All right. If there is no question, so let's continue. Now, since the distance is small, so how to make it exactly L? So sometimes we need to reuse some item that we have removed before. And sometimes we need to remove an item or remove some item that we are currently use it, right? To make it exactly L. And we will use knapsack to make it exactly L by adding these items. But you know, the item might be large since A is up to 10 to the 12. But since we only need to increase small value and maybe we can prove it using the Pantin equation. So in fact, we will never we will never use more than m square. So in our knapsack, we can just make the state is from minus m square to plus m square. Alright, the state is only from minus m square until plus m square. And the answer is in L minus current value. Is it correct? L minus current value, because we need to add this value. So the result is the current number of item we use currently added by dp this. Maybe the current number. This is the current uplift. I think we need CND, for example, the current number of item added by dp L minus current uplift. And since we only want to add from minus m square and plus m square, so for each item, we only need to use at most m square divided by wait, m square divided by that value, right? Because if greater than this, we will never use that since it is out of bound. So the number of item is smaller. Is it correct? Even the number of item up to 10 to the 12, but using this observation, we just need to use a few item only. Even we can optimize using 1 to 4 parts like that. We can divide this into 1 to 4 8 and so on, so we can make it smaller. So the number of item is smaller and we can use knapsack here. And also for each item, actually we need to do this. For example, the number of item is A, and we are using all X item, for example. Okay, so it means we can only remove item, right? We can only remove item. It means we can just add this item to the knapsack. For example, the value of this is I, so it means we have an item that is the weight is I and the value is 1. And then what else? And then the number of item is X. I mean A. X is equal to A. And maybe we can minimize with m squared divided I. Alright, is it correct? And maybe some item, wait, sorry. I think it is -1 and minus I minus 1 because we can only remove the item. It is when x is equal to a. What if x is equal to 0? It means in that type we use nothing. So we can only use them. We can only add them. So it means it is positive. Otherwise, x is between 0 and a. It means we can do both of them, either removing or adding, right? So it means we need to add this. Wait. Minus I minus 1. And the number of item is a minus x, right? And you can minimize with this as well. And we can add, sorry, I think this is removing. Removing means we can remove x. And for adding, we can add at most a minus x. Is it correct? All right. So that is the general idea. All right. Is there any questions about the solution of this problem? Okay, the time limit is 4 seconds. Even in OC, it is 5 seconds. All right. So the the whole steps of the solution is, at first we can greedily use all of them. Use all of them. And then we can make it closer to L. Again, using greedy. We will remove from the largest. Just greedily remove from the largest, as long as it is still less than L or still greater than L. So after these steps, the current uplift minus L, I mean the absolute difference, always less than M, right? Because we have do this. If or it is impossible. We can check whether it is impossible or not here. If L is out of our bound, it means it is impossible. All right. After remove the largest, we will use knapsack. And in our knapsack idea is like this. At first, we will check for its type of items. And we can or we need to handle about adding an item and also removing an item. So for example, we are currently using X item in this type, and there are A item. It means we can add at most A minus X, and we can remove at most X. All right. So it means there are this item, this number of items, and we need to optimize by bounding this. Just minimize with m squared divided by I, because if it is greater than that, it is redundant. It is out of bound. And then we can make the state is from minus m squared to m squared. And then we can split the items into 1 to 4 8 parts, and then the rest, right? It will make it smaller. All right, and finally, the answer is the current number of item plus TP L minus current uplift. But note that if the TP is still minus infinity or still unvisited, it means it is impossible. Sometimes it is impossible. For example, like this, we cannot make it exactly 5. Even 5 is between the largest and the smallest, but we cannot make it exactly 5. So we can know it from the knapsack. All right. So this is the solution. Is there any other questions? All right. Welcome. Okay. I think I need to add the problem to the repeating. And also, I think there is another contest we haven't discussed it before. Okay, yes. I think this is the Friday contest. And what was your score in this contest? Can you mention your score? Okay. All right. Okay, then you can submit it. Submit your accepted solution to the repeating. Right. How about Ahmed? Do you know Ahmed's score? Or okay, I can ask him directly. Okay. How about Saram? How many score you got in this contest? In Friday contest. Alright. Yes. Okay, I will confirm it. And how about Saram? Okay. So maybe most of you know the idea for the first. I think the second one maybe more more users got accepted. It's about 3, right? 3 and rerouting. Okay. Yes, I think we will discuss it sometimes. But I think for today, that's all. Because Isha time has come in my city. So see you later, maybe in Friday. Will you have a contest in Friday? If you have a contest, maybe you can solve this contest, the TOI day 2. Alright. I think you haven't tried it. Try it, right? Alright. So see you later, maybe in Friday, inshallah. And thank you very much. Let's close our meeting with praying. Subhanakallahumma bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik.